Have we all written it down? I see people who are not writing anything. If it's because you can't remember, that's okay. I will forgive you. No problem. See if you can get the next word. And it's okay if your definition doesn't sound exactly like mine, as long as it includes the same kind of stuff. Yes. Yes. See if you can get the next word. It could be change, it could be stress. Either of those will work. Okay?
Bless you.
Okay, so you could use the word change if you prefer. Okay. What will the system do? Shift. In order to and there's a couple ways of saying this. You could say minimize, or you could say counteract the stress. So actually, I'm going to put the word equilibrium in red as well, because those are your key words. And if you wanted to make it even simpler, you could just say if a system at equilibrium is stressed, okay, instead of saying is subjected to a stress if you wanted to. The system will shift in order to minimize or counteract that stress. Now, Le Chatelier's principle is a funny thing because it's not really an explanation. If you want to truly explain a shift, you need to talk in terms of rates. Rates really tell you why the system is making more product and using up some reactant. Le Chatelier's principle just says it does, and it kind of makes up a made-up reason for it. That's why it's called Le Chatelier's principle and not something like Le Chatelier's law, okay? Because a principle is just kind of like, it's just a principle. I don't know. It has a different meaning in terms of science, okay? However, you will be asked to explain things either using rates or using Le Chatelier's principle, and you need to be able to explain either way, okay? Because Le Chatelier's principle is used all the time, even though it's not as good of an explanation. It's a really fast way of predicting shifts, and it's really effective at, you know, just getting to the end, okay? So in general, I don't know if you remember this from yesterday. We're going to just bop up here for a minute. If we increase the concentration of a chemical species, so let's say I have A plus B goes to C plus D. If I increase the concentration of A, will that cause the equilibrium to shift towards A or away from A? Away from A. Now, what if I were to decrease a concentration? Would that cause the equilibrium to shift towards A or away from A? Towards A. Okay. So again, that's not an explanation. That's just a quick way of predicting things. Okay. So if we increase a concentration, it shifts away. If we decrease a concentration, it shifts towards. Now, some of you are not going to like this at first. That's okay. You never have to use it. This head to tail method. Okay, some of you will look at it and go, it doesn't make any sense to me. Just try it for a while. My AP class didn't like it when they were first introduced to it, and then they came to love it. You may also come to love it because it's a super fast way of predicting the direction of a shift. Okay, and in fact, what we've done up here is I've shown this head to tail method of the arrows. I had an increase here. There's the head of my arrow. Yes. And then I attach the tail of the arrow and I go across I make sure that this arrow goes across the equilibrium arrow. Okay, I mean, it has to go across to the other side. And if you do that, it will predict the shift. So, for example, down here, I put a downward arrow, okay? That puts the tail of the arrow up here. That means the head of the shifting arrow needs to attach to that tail because it's always head to tail. And that means that it's shifting left because the shifting arrow has to go across the equilibrium arrow. Okay? And like I said, if you have that look on your face, that's okay. You might look at this and go, this makes no sense at all. But it will eventually, okay? So how do you do this head to tail method? You write your reaction, you draw an arrow representing either an increase or a decrease, and you write it above the species that's changing in concentration. Then you're going to draw a shifting arrow either this way or this way. Okay, so that's a shifting arrow. So it attaches to the top of the first arrow. So if I have an up arrow and my equilibrium is here, I have to attach the arrow to the top of that arrow, and I have to put it over the equal sign. And where would I put the pointy bit of that shifting arrow? Would I put it on the left-hand side, or would I put it on the right-hand side? This is called the head to tail method. I would put it on the right-hand side because if I put it on the left-hand side, is that head to tail or is that head to head? That's head to head. So that's what I don't want. Okay, so I want my head over here. So if I increase the concentration of a species, it's going to shift away from that increase. Now, if I had an arrow here, and I have an equilibrium arrow here, whoops. My shifting arrow is going to have to go over the equilibrium arrow. Where will the arrowhead go? Will it go on the left or will it go on the right? It will go on the right. And look, that would be shifting towards a decrease. And like I said, don't worry too much if this doesn't make sense right now. We're going to use it in context a whole bunch of times until it makes more sense, okay? Because learning things out of context is sometimes confusing. All right, so other ways of quickly knowing which way an equilibrium is going to shift, it always shifts away from an increase. A and I are both vowels, okay? Up, up, and away. So that's an, oh, look, an increase. It shifts away from the increase. Now, it also shifts towards a decrease. Toward T and D are both consonants. So that might also help you. So we're just going to practice putting in some arrows here. All right? So the first thing you need to do is you need to draw the line across the equilibrium arrow. So you need to make sure that the equilibrium arrow falls underneath that line that you have drawn. And then the second thing you need to do is you need to put an arrowhead on that arrow. You need to decide, does the arrowhead go over here or does the arrowhead go over here? Do you think you could try these? Give them a try and then we'll go over them together, okay? And if you're really confused by the whole thing, call me over. Because if you're like, I don't even know what arrow to start drawing, that's not a good place to be. Anyone want a hand? Okay. And if I don't see you writing, I'm going to assume you don't know what you're doing, and I'm going to come over and help you. You finished? Okay. It's very much like that. It's very much like that. Yes. That's it. Right at the top. Yeah. Now, perfect. Let's see. Is that one okay? Beautiful. How'd I go? Good. How'd I go? Good. And then draw the line over top of the arrow. And then I'm going to say there's the line to go over here because the line has to start at the top of the arrow and have to go over the top of it. Okay. And then you say that's right. Yes. Okay, and all we want to do is yeah, that way. I mean, you've gotten going the right way, so that's not. Yeah. Okay. So just check your work up here. So if I say we increase the concentration in H2, you can easily say we shift to the right. If I say we decrease the concentration of HI, you can easily say we shift to the right. If we decrease the concentration of I2, now this one can cause problems because sometimes people want to make the arrow go that way. But remember, it has to go over top of the equilibrium arrow. Okay, so, and it has to start at the top of that arrow. So we're going to draw it that way. And that means our arrowhead has to go that way. So if we decrease I2, it has to shift to the left. And if we increase HI, it has to shift to the left. All right, so that's one fast way of predicting. It's not the only way, but feel free to use it if you like it. If you hate it and you never want to use it again, that's okay. All right, it's fine. So here we're going to look at the difference between explaining shifts in terms of rates and shifts in terms of Le Chatelier's principle. So here we have the reaction. All right, and what we are going to do to this reaction is we're going to add some NO. Okay, now, if we add some NO, we can easily predict that this thing is going to shift to the right. Yes? Okay, so the stress was an increase in NO, so the system shifts right. And here's the language you're going to use if you are explaining in terms of Le Chatelier's principle. The system shifts right in order to, okay, so in order to, and then you're either going to use the words make more or use up. So what have we done to this? We have more NO than we started with, yes? Then at the start. So what does Le Chatelier's principle say? It says if you stress a system, if you have more NO than you had before, you need to bring it back down again, right? If it's like, oh, you made it higher, it needs to come back down. Whatever, and this is, don't ever write this as a definition for Le Chatelier's principle, but what did Hebden say? Whatever you do, nature tries to undo. Okay, it's a good way of thinking about it, but do not write that as your official definition. Okay, so therefore the system shifts right in order to, are we going to want to make more NO or use up NO? We want to use up NO and bring the NO back up or down. We want to bring it back down. So the other language that we're looking at here is we want to bring the whatever back either up or down, okay, to close to its original value. And if you remember last day, it doesn't actually get to its original value. It never crosses there. It gets close, but it never quite makes it all the way. So that's how you explain in terms of Le Chatelier. It is short, it is to the point, you're done in one sentence. Kind of nice, yes? Rates. Oh, look at this. Oh, 1, 2, 3 sentences. So much more words, so many more words. So let's do it anyway, though, because it actually makes more logical sense. It really explains what's happening. So when we increase the NO, that means that the forward rate is going to increase. And we want to say why. Why does an increase in concentration of NO cause an increase in the forward rate? We get more frequency of collisions. So due to an increase in the number of collisions between, and who's colliding? You don't have to be specific here. You just have to see between reactant molecules, okay? What happens to the reverse rate when we increase NO? Nothing. So the reverse rate stays the same. So what you're describing is you're describing first what happens to the forward rate, second what happens to the reverse rate. Because the concentrations of the products stay the same. So you say what happens to the forward rate, you say what happens to the reverse rate, and then you say how does the forward rate compare to the reverse rate? So which one is faster now? Yeah, so the forward rate is faster than the reverse rate. So since the forward rate is faster than the reverse rate, are we making reactants or products faster? Products. Faster than we're using them up. And if we're making products faster than we are using them up, that means the system is shifting to the right. So we could say we start at equilibrium. The forward rate gets faster. The reverse rate stays the same. And then eventually, this is at the stress, and then the shift occurs. And then we get both arrows the same again, but a little bit bigger than before. You're not going to have to do this, right? I'm never going to ask you to do that, but it helps you possibly to think about it. So we're going to write it down. Do you think you'd be able to do the next one on your own? Give it a try. Use the one above it as a model. And when you're done with that, you can go on to the next page and do D. Okay? Yes. Okay. So we're going to look and we're going to say, what's happening here? The system. Yeah. So this one is based on this one. Okay. Rest of the system relies in what You're like me, I always say the wrong one. I think the right one and then I say the wrong one.
Please excuse this interruption. We would now like to call down the letter K for the Great Canyon Unionization. Again, that is letter K.
The strength of the system was a decrease in concentration. Okay, how'd that go? Yeah, looks good. Now you can try that one. If you finish that one at the bottom of the page, flip and do the one on the next page, which is the, what you call it? Great explanation. You good? No, you're good. Yes. Okay, so here's what our so we want to raise opposites. So we want to knock it down, we want to bring it back. Yeah. Yes. Yeah. Because what's happening is the stress to the system says, oh no, there's not enough H2. You took away some H2, get it back. Right? And so it says, oh, I'm going to take more H2. So it's going to come back. Exactly. So check your answer. I think most of you were getting it, but you can check your answer from page 33. See if you got that correct. And then make sure you're trying the next one on page 44, if you haven't already. Yes. Oh yeah, we could back up to, we could say close to the original value. That would actually be better. It's been pointed out that I forgot to say too close to its original value, which I should have. Probably, yeah. There we go. Yeah.
Stress is so that doesn't make sense.
No, it doesn't make sense. Yeah. But you could say the H2 in the system was decreased. That would work. Yeah, and that would be okay because you've implied that that was the stress. Okay? Yeah. So that would be fine. Yeah. Okay, so when the H2 is decreased, the forward rate decreases. Now, if we have less of this, why does that make the forward rate slower? think back to last unit.
Less interaction.
Fewer collisions, yeah, exactly. Okay, because there will be fewer collisions between NO and H2. Yeah, okay.
It's the opposite.
And that's the reverse rate. Ah, the reverse rate. What have we done to these guys? Did we? All we did was remove H2.
Oh, they stay the
So
same.
they stay the same, and if they stay the same, what happens to the reverse rate? It stays the same.
Oh, eight piece, yeah.
Yeah, okay. Does anyone want me to check their answer in terms of the rates? Or should we just put it up here? Let's put it up here. When the H2 is decreased, what happens to the forward rate? The forward rate decreases. Why? Because there are fewer collisions. Between NO and H2. Everybody, let's wake up. Everybody, what happens to the reverse rate? Stays the same. Why? Because we didn't do what? We didn't change the concentration of the, and we call them the products, okay, because they're on the right-hand side. We didn't change the concentration of the products. Since the, and now we've lowered the forward rate, but the reverse rate has stayed the same. So which rate is faster now? The reverse rate, since the reverse rate is faster than the forward rate, we are making products faster than we are using them up, and the system shifts right. Did I do that wrong? Ms. Spence is a dummy. Since the reverse rate is faster than the forward rate, we are making reactants. Oh, that's better. And then the system will shift to the left. Sometimes my brain doesn't brain very well. Yes?
Forward rate is slower than
Yes, and it's totally okay to say forward rate is slower than the reverse rate. It doesn't matter as long as you're getting the idea that this one's bigger than that one and vice versa. Okay, so your reaction arrows would be, oh, we start at equilibrium, and then we have the stress. And then we have the shift. And then we have our new one where they're slightly smaller than before. Okay, so you have a convenient little script here. If you are good at making explanations on your own, you will not need to use the script. If you find it hard to come up with an explanation on your own, then you will want to memorize the script. Do you know what I mean? Like, so if you find it difficult to put the words together, then just memorize the script. If you're okay putting the words together, as long as you have all those ideas, it doesn't have to look exactly like that. All right? But you need to have all those ideas in there. In the rates, you need to be talking about collisions. You need to be comparing the rates. You need to say which way you're shifting, all of that. Okay? So there's some exercises here which we are not going to do because we need to press on, always pressing on. To 2.2c on page 38. Okay, now I'd like you to think this through. As we decrease the volume, what happens to the pressure? It increases. Now, what that means is that as volume goes up, pressure goes down. And that is called an inverse relationship. So pressure and volume are inversely proportional. And one way of writing that, you don't need to be able to do this for Chem 12, but you will see it in university. So I'm going to say that volume, or sorry, actually, I'm going to say that pressure is proportional to this little fishy symbol here. That means is proportional to 1 over volume. Okay, so that's really all you need to know as background knowledge for this. And let's look at shifting from a rate perspective when we have gases. This only matters if you have all gases, okay? It doesn't matter if you've got other things, but we're mostly going to have gases in this unit. So if we decrease the volume, here's our system here. So if we decrease the volume, what happens to the pressure? The pressure, everyone, increases. If the pressure increases, what happens to the rate of the forward reaction, and why? And if you're having trouble thinking about that, we have a lovely little picture up there showing what happens when the volume is decreased. And I want you to think what doing that would do to the rate of the forward reaction. It's going to increase it. Yep. So the rate of the forward reaction increases. And the question is then why? And when you're talking about why, you always want to be thinking about collisions. Okay, so think about collisions and think, why does squishing the container make the rate go faster? There will be more collisions because there's the same number of particles in a smaller space. What happens to the rate of the reverse reaction? It increases. Why? And all of you who are not answering this question, you're sitting there knowing the answer, not answering it, you should be ashamed of yourselves. No, I'm kidding. Why do we also have the reverse rate increasing? Because once again, what have we done? Squish the container. So we have the same number of particles in a smaller space, therefore we have more collisions. And why? Same reason as above. Okay, more collisions because we have the same number of particles in a smaller space. Now, this is where it gets a little tricky. Which rate of reaction is increased more? Is it going to be the forward or the reverse, and why? And in order to help you think about this, I've drawn a little picture showing the reactants and showing the products. So over here, we have 4 reactant molecules, yes? And over in the products, we have 2 reactant or product molecules, I should say. So you are increasing the rate, you are increasing the concentration essentially of 4 things on the left, even though the H is like all the same. You can say I increase one H2 3 times, and I could increase the second H2 3 times, and I increase the third H2 however many times. So I'm essentially increasing the concentration of 4 particles on the left, and I'm increasing the concentration of only 2 particles on the right, which is going to make a bigger difference. The side with the more molecules, okay? So you're never going to have to be able to explain that, right? You're not going to have to describe why that is, but as long as you kind of get it, that if I have more molecules, I've changed the concentration of more things. And if I've increased it, I've increased 4 things, which is going to make more of a difference than increasing only 2 things. Okay? So the side with more gas molecules experiences a greater change in rate. Therefore, which rate will have the greater increase, forward or reverse? Forward. And if the forward rate is now bigger than the reverse rate, which way are we shifting? We are shifting right. Okay, now, we don't have to go through all of this. If you feel okay with the fact that if I increase volume, I've changed the concentration of more things, so it just increases more. So we don't have to go through that. Yes? What I'm saying is that you've increased the concentration over here. I've increased the concentration of N2. And I actually have 3 H2s, so I've increased the concentration of H2, that first molecule, okay? I've increased the concentration of H2, and I've increased the concentration of H2. Over here, I've increased the concentration of NH3, and I've increased the concentration of my second NH3. So because I've got 4 things increasing in concentration here, that's going to make more difference in the number of collisions than if I'm only increasing 2. Whoa. Where to go? Are we on 2.2b? Yes. Okay. Whew. Nope. We're on 2.2c. Okay, there we go. Sorry about that. it's going to make more of a difference because I've changed more particles concentration than on the right-hand side where I've only changed 2 particles concentration. So this is going to increase more. This will increase, but not as much. Did that make sense? Yeah, yes.
All the concentrations increase because of the pressure.
Because I squished the container. Because whenever we're changing the pressure, at least in this course, we're always talking about a volume change. Okay? So we don't have to go through all of this. If you want to, I can post the video where I did it with my AP class, but I don't think it's necessary. Okay, here's a more mathematical way of doing it. You can take a look at it if you want to. Again, you don't have to understand it. Basically, if I didn't explain everything to my AP class, they'd be like, but why, but why, but why, but why, but why? Yes? And so I was like, okay, I'll tell you why, I'll tell you why, I'll tell you why. So if you want to, come talk to me about it, but you don't need to. So in other words, we increase the forward rate more. So this is page 40, halfway down the page. Page 40. Halfway down the page. So now what we're going to do is we're just going to look at what happened. So we have the original rates before we squished it. So the container was bigger. Now the container is smaller. And so the forward rate increases a lot because we have 4 particles. And the reverse rate also increases, but not quite as much because we only have 2 gas molecules. And that makes the forward rate greater than the reverse rate. Therefore, we're making products faster than using them up. And therefore, we are shifting to the right. Is good? Okay.
Excuse this interruption. If you could please send down letter L for immunization.
Aren't you guys glad you're not in grade 9 and don't have to get your shots this year? Although I have to be honest, like I'm kind of a vaccination junkie. Like I'm really, really happy when I get to have a vaccination, right? Because it means that I'm not going to get whatever disease it is, right? So when I turned 50, I got the shingles vaccine because when I was, you guys won't have to worry about the shingles vaccine because you've been vaccinated for chicken pox, or at least I hope you have been. But if you were back in the day, there was no vaccination for chicken pox. If you got chicken pox, then the little virus goes into your cells and it hides there and it waits until you're like 30 or 40 or 50. Usually it's after 50. And then it comes out as a thing called shingles. And what it is it's this like, it apparently feels like burning on your skin. Like I've not had it because like for my 50th birthday, I literally asked for the shingles vaccine. I'm like, for my 50th birthday, I would like to receive the shingles vaccine. So that was my birthday present that year. Happy 50th. Yay. It's quite expensive. It was a couple, like $200-300. I can't remember. But anyway, okay, let us now graph what happens when we decrease the volume of the system. And we're starting with a rate diagram. So we're going to have our rate over here. And we're going to have our time over here. Forward. Reverse, forward, reverse, and now we decrease the volume. We go from bigger to smaller. And remember the forward rate. What happens to the forward rate? It increases. What happens to the reverse rate? It also increases. Does it increase as much? No. So I'm going to have it go up only part way. And now the two rates are different. This was our stress. We decreased the volume. That was our stress. And now the system is going to shift. And remember, what kind of shape do we see when we shift? We see a curve. Yes, when we shift, we see a curve? No? Yeah, isn't that a curve? Curve? What did you call it? Oh yeah, the top should be sharp. You're absolutely right. You're right. Now, here's going to be where we come into a little bit of like what's happening with the sharp business that you didn't tell me about, Ms. Spence. Okay, so let's watch. The forward one is easy to do, okay? Because forward, I'm just going to have them meet in the middle. Sometimes they meet in the middle. Sometimes they meet higher up. Sometimes they meet lower down. It really doesn't matter that much because we're only sort of qualitatively doing this, not super quantitatively in terms of rates. Okay, so there we go. That's our forward. Now, the reverse, it's going to have to go up. So I'm not actually going to see like a sharp little point there because it already went up. It is now going to continue going up, but instead of going straight up, it is going to curve up. Okay? So it's going to curve up. Let's make that bigger so we can see it better. Okay, so the section from here to here, that is our shift. Okay, and you can see there's no lovely little point there because it already, if something is going up and then it goes up some more, you're not going to see a sharp little point. But remember, you should never use an S-curve. No S-curves ever. All right, except for when we get to acids and bases, and then we'll have S-curves in our titration, but that's a different beast. So that's our rate diagram. How are we feeling about that diagram? Yes? Yeah, I just haven't drawn it very well. Like the shape of the curve, they should be mirror images of each other. Like this part here should be a mirror image of this part here.
When they're straight, like
Yeah.
they're the same line.
It should be on the same line. It's just, I can't draw them over top of each other, so I just draw them right beside. Yeah. Yeah. Okay, let's do a concentration diagram. Does it matter where I put my initial concentrations? No. However, I have to think, I'm shifting to the right, so NH3 is going to go up, so I don't want to, and N2 is going to go down, so I don't want to put N2 too close to the, or H2 too close to the origin, because otherwise they're going to like drop below. So I'm actually just going to go N2, H2, NH3. On a quiz or a test, you will always be given like the initial concentration, so you won't have to make up where they go, okay? This is concentration, molarity versus time. And right here, we decrease the volume. Now, this is where I become unhappy with concentration diagrams. Unhappy, Ms. Spence. And the reason is that in order to do this actually accurately, I would have to, if I shrunk the container by half, I would actually have to double each concentration. Double. Can you imagine doubling the N2 concentration? Does that make sense to draw that? Or are we going to run out of room? We're going to run out of room. So what we do is we just fudge it a lot, okay? So we just fudge the stress change. Okay? We just kind of say, okay, I know they would all double, but I'm just going to make them all go up a bit because then they will fit on my graph. Okay? They all go up a bit because I've squished the container, all the concentrations go up. And I don't worry about how much they go up by. Yes? Yes. I'm just arbitrarily, that's just set randomly, okay? Don't worry about how much the stress change is, just they all go up. All the concentrations just increase so it fits on the graph. Okay. So we have squished the container. Which direction is this system shifting? It is shifting to the right. All right. And so the N2 concentration is going to, so as it shifts right, the concentration of N2 is going to decrease, and the concentration of H2 is going to decrease, and the concentration of NH3 is going to increase. Okay? And so let's graph this now. We're shifting to the right. The N2 is going to decrease. This is a shift, so it's going to be a curve. I'm just making up an amount. And I made that one relatively small because the coefficient of N2 is 1. What is the coefficient of H? 3. So H is going to go down by how much? 3 times as much. This here, this distance is going to be X. H is going to go down by 1, 2, 3x. So I want to end up down there. Whoops. And then NH3, maybe I'll pick a different color for NH3. NH3 is going to start here. Okay, I'm just going to put like a little dot there so you can see, oh, that's where it's starting. And it's going to go up by how much? 2x. So from here, it's going to go up by 1, 2x. Okay, so it's going to end up there. Is good? Okay. So notice that a change in volume makes all the concentrations change. So that's stress When you change a volume, the stress, all the concentrations change in the same direction. So when the stress is a change in volume, all the concentrations change in the same direction. We don't worry about the stress change, but we do worry about the shift changes being proportional to the coefficients. Okay? And I'm going to send you home to try out this simulator. Okay? So you're going to go home and you're going to do the simulator and try and fill in pages 42, 43. Okay? So the homework, number 1, try the simulator. And fill in pages 42 to 43. Second thing you're going to do is we'll backtrack to concentration and have you do the exercises from there, which are on pages 35, 36, 37. Yes, absolutely.
I don't know, I magically lost my pencil that I was using this morning.
It happens. Here you go. In fact,
Great,
you
thank
can
you.
keep it.
Oh, thank you.
Okay. Yes. That is proportional to. You have to listen to that. Okay. You just need to know that volume goes down, that it goes up, that volume goes up, that it goes down. What that means is that with the volume in the process like that, yeah. Oh, yeah. Hi.
I can't really tell if these numbers when they're decreasing and increasing.
Okay, so if we are shifting to the right, which is what we're doing in this case.
Yeah.
Okay, and we figured that out before, so if you don't remember why, you can go back and look at that. If we're shifting this way, what that's doing is it means we're using this up and we're making this, we're using this up and we're making that. That's what shifting means.
You decrease and
Those will decrease and that'll increase. If we were shifting the other way, we would be using this up, this would decrease, those would increase.
okay.
That makes sense?
Yeah, I got it.
Cool, cool.
Thank you.
Oh, thank you. Your test will be marked by tomorrow. I'm getting there. I'm getting there.
Because we were like, we traveled number 13
Okay.
more, so we need the test for the check.
Oh.
After
Maybe. Maybe. Sucks. But we'll see. I need to teach as fast as I can. I live water. Yeah. Alright? Yeah.
thank you.
Are we gonna finish this meeting before
we break the end step. Yeah.
please we have time to study like I see the face and
That is exactly it. So there is a bunch of people.
good. Better than not like it, right?
Yes.
Have
So
our faces and then
ask today's ask today's ask this part. And then oh, so yeah, we'll see how much we're up to get.
so like you're doing 4, 3, 5.
And the reason is that Mr. Holder does a really good job of teaching those things, and I have good worksheets that go along with those particular things, right? Whereas if I was to do solubility, I would need to rewrite the workbook in order to do that. So, yeah.
Big change is not hard.
Phase 2 and electrotest. So you finish the unit, you finish the year with some hard students.
Isn't it a good time for shortness?
Yeah.
I know it's the hardest because my friends back home
Yeah.
in grade 12, they were doing it. They're doing it in 1 year. One course you're doing it here, you're doing it in 4 years.
Yeah, Tyler will teach you from
Good, good.
Tyler's back,
I remember him.
right? Yeah. No. Tyler will be back in electrochem, not yet. Yeah, I know, we gotta wait till unit 6. I know. It will be. Tyler's man.
Yes. Alice the goat.
I didn't know what that was until this year. I was like, why are people like, what's with the little goat emoji?